hyperbolic tangent of z is a hyperbolic sine or its primary hyperbolic sine over hyperbolic cosine. And then how did we define a hyperbolic sine of z? That was e z e minus 0 to, and hyperbolic cosine so in the end hyperbolic tangent of z is just going to be like that. So we need to show that the poles here are, the singularities are poles. We determine the multiplicity and we compute the residue. To help you figure out the multiplicity, now a pole is usually in here. Any value of z that will make the denominator 0. So it's going to be a 0 of the denominator, and you want it to be a 0 of finite order, which would be the multiplicity. Finite order 0 means it's a 0, maybe a 0 of the derivative, and a 0 up to a certain order at one point, it stops to be the 0 of the derivative. That's how you determine the multiplicity. The highest order derivative for which the z is still a 0 of the derivative, it's still a 0. So a multiplicity 1 4 is going to be a 0 of the denominator, but not a 0 of the derivative of the denominator. So a pole of multiplicity 2 will be a 0 of the denominator, which is also a 0 of the derivative of the denominator. So that will be multiplicity 2. In other words, the denominator is able to be written as a z minus z0 times something that has no 0 in that post. All right, so let's work on this one. So to determine the potential poles, they're going to come from this. That's all you have to solve and find the potential poles. That means really hyperbolic cosine becoming 0. How can hyperbolic cosine be 0? Well, you tell me, is it possible or it's not? Let me remind you, these are functions of this variable. These are not real functions. I'm not sure that it's not. Just try to solve and see if you can find a solution. These are complex variables, and many things have been shown to be possible. So no pause yet? I will find the pole by solving this equation. Exponential 2z equals exponential pi I. What are the solutions to this? This is exactly when hyperbolic cosine becomes 0. Does anybody know where the poles are? half is not correct, Baruch. But pi half plus k pi, and I again, why are you putting that I? What do you need I for? Are you sure you have an I in there? I guess, yes, you probably have it. So the micro is better. The micro's answer is better. Is better. It's more complete. There are many, many poles, infinitely many poles, not just one. Right. Remember what this means. If you have this, it means that 2z must be pi I plus 2k by I, any multiple of 2 pi I, because exponential of 2 pi I is 1. So the 2z doesn't have to be exactly pi I. You can add any multiple of 2 pi I. So let me write it better. Any integer multiple of 2 pi I. K here is 0 plus or minus 1, positive or negative integer. So we are looking for z. The poles are pi half I plus k pi I. And that's Michael's answer. These are all the poles. I know they are poles and they are order 1 because the derivative of these are zeros for hyperbolic cosine. When I take the derivative, it's a hyperbolic sine. And when I plug in this singularity, it's not it doesn't make it 0 anymore. Hyperbolic sine of pi half plus k pi I is not 0. So that makes it a pole of order 1. It's a 0 of the denominator, but it's not a 0 of the derivative of the denominator. So pi half plus k pi I are simple poles. Now, problem we have here, we cannot factor hyperbolic cosine, so you're going to have to come up with a better way of figuring out what the residue is. And here, I'm going to need another result. Let me tell you what it is that's going to help us here. I will prove it later, probably next time we have a class. So next Monday will be just a test. So the Wednesday after that, I can prove you that. So if f of z looks like P of Z over Q of Z. Right? And Q of Z0 equals 0. So Z0 is a singularity, but Q prime of Z0 is not 0. That makes a Z0 a pole of order 1. That's another way of saying that Z0 is a pole of order 1. It's important that P of Z0 is not equal to 0. If it was 0, we just include it in Q. So all of these make Z0 a pole of order 1. And I'm not assuming that QZs are polynomial, so I don't have the factoring tool here. Remember those those poles, we're gonna use them later. We're gonna compute the residue soon. So very importantly, under these conditions, residue is equal to Z0 of this kind of function is really P of Z0. That's very important. We'll prove that next week. But we're gonna use it here because there's no other way we can handle it. So let me again remind you what we have at hand. We have a hyperbolic tangent. Easy E minus Z, easy plus E minus Z. We have found the singularities ZK, which are pi over 2 plus K pi I. They are 0 over EZ plus E minus Z, but not 0 of its derivative, so these are simple poles. But most importantly, the Q is EZ plus E minus Z, and the P, the EZ plus E minus Z is our P of Z in this new result. Q of Z0 is 0, but its derivative is not 0 at those, because they are simple poles. So we are in the conditions of that statement here. We can use it to compute the residue when Z equals pi over I, not pi over I, pi over 2. Plus K pi I of EZ E minus Z over EZ E minus Z. This is going to be, so I need to read here. Tell me what I should put there. Is the numerator add this poles divided by the derivative evaluated at that pole. So what what do we expect here? Let me use the zk. What happens when we take the derivative of ez plus e minus z? We get ez minus e minus z. This is what the residue is going to look like. And we just need to simplify it. Just put all the zk's are, and it's a review of the elementary functions. So we have e I pi over 2 plus k pi, e minus I pi over 2 plus k pi over e I pi over 2 k pi. I did something wrong. Let me see what I messed up. What did I mess up? Because it was supposed to be something simple. That's right, micron. So here is where here I'm dealing with this. This should be a negative. All right? And if this is the case, then we don't have to do much. We're going to have an easy k minus, so numerator and denominator are the same. I don't need to do any work. This is 1. I know the denominator is not 0, so, I mean, none of these is 0. So, I didn't need to go this further step. Right, so this is a formula that we'll need to remember. And we'll come back to it. Sorry, I'm erasing. It's a formula, a general formula, when you have a simple pole of a rational expression. Unfortunately, it doesn't expand if the pole is multiple, unless you have a rational function, meaning a p and q being polynomials. All right, so that was C. And we're going to go back to the simple case. Now, I'm looking at f of z equals ez over z squared plus pi squared. Again, find the poles, determine the order, and compute the residue. from Baruch. I see I pi and negative I pi. These are the singularities. Okay, I agree with that. Now, can you compute the residues at those? They are going to be simple pairs, as you can see. They make the denominator 0, but not the derivative of the denominator 0. A simple pair. Now let's compute the residue at each. Right, it's a simple pair. This is a type of P over Q. We can apply the result I just mentioned, or we can factor z squared plus pi squared. We have a choice here. So let me do the factoring first. So we get z plus I pi, everything over z minus I pi. That's what we call the phi of z over z minus z0. You remember that form. The residue is determined by phi of z. In this case, for a simple pair, we're just going to have a phi of an I pi. And what I called phi was easy over z plus I pi. So all I need to do is E I pi over, I'm evaluating phi, I pi plus I pi. And Baruch is telling me something. You think it's going to be I over 2 pi? I believe so. So e to the I pi, you should know this is -1, and 2 pi I, we just put in the standard form of complex number, minus I over 2 pi I squared. You just multiply by I on both numerator and denominator. And that's going to be negative I over negative 1. So you're going to get I over 2 pi. That's the value of the residue. Now let's repeat this for negative I pi. To imitate this. So negative I over 2 pi is the other one. That's exactly correct. Yes. So residue is equal to negative I pi. This time is going to be EZ. I'll use the other factor, Z minus I pi. That's going to be the phi when I make Z equals negative I pi. I'm going to switch those two. They switch role. So the current residue of it was easy is going to end up to be E negative I pi over negative 2 I pi. E to the negative I pi or E to the I pi, same thing, it's negative 1. Let's use the Euler formula. So you get 1 over 2 pi I, and when you put in a standard form, multiplying by I, you get negative I over 2 pi. That was odd. It was not part of it. So this one goes right there. All right, let's get this one correct. So now we're going to deal with f of z. This is a part of E. Z over cosine z. Let's find the poles and compute the residue. Just a reminder, cosine z is defined by eiz e minus iz over 2. Right, Baruch, find what the singularities are. Pi over, let's see. Well, yeah, you can put it a negative pi over 2 plus k pi. Yeah, why not just pi over 2? But there's nothing wrong, but yeah, just pi over 2 plus a multiple of pi. Right? The other one was okay also. You just need to pick appropriate value of k you get. So the poles are pi over 2 plus k pi multiple of pi. Now we want to compute the singularities at those numbers. Make sure, so to find, this is how we found the poles. As I did, similar to something I did earlier, we need that to be 0. And usually multiply by eiz. So you get 1 here. And then you put everything in exponential form. Negative 1, that's ei pi. And that's how you get a negative 2. Pi is negative 2. That's supposed to be I, sorry. So I 2z should be I pi plus 2k pi I. Each time you exponential 2 pi I, multiplying by 1. Two z must be pi. And when you divide by 2, then you see pi half. So these are the singularities, these are the poles. And you can see none of them make sign z 0, so it's a simple pole. Multiplicity 1. So now we're going to use that formula I gave you that I will prove you next week to find the residue at z or cosine z. This is the type P of Z over Q of Z. You see P of Z is non-zero. Q of Z is 0, but Q prime of Z, they call that a ZK. Cosine is 0, that's what makes it a singularity, but the derivative of cosine, which is sine, when you evaluate it, is not going to be 0. So it's within the hypothesis of the formula I gave you. The residue here is supposed to be Z over cosine prime of Z. You make a Z equal Z0. So all we need is do the Z. It's not a Z0. I label them Z sub K, the pole. Should I have a negative there? Of course, yes. Actually, yeah, I guess. Make sure of that. So we're gonna have E I minus E minus I pi r plus K pi over 2I. If you work out the simplification when you have time, this is what I found. Let me just do it completely. So let me finish out this. So residue when Z equals pi half plus K pi of Z over cosine Z is supposed to be negative pi half plus K pi, that's the Z, over sine of that, so I'll have E I pi half plus K pi minus E negative I pi half plus K pi over 2I. So I keep the negative here. And I have also a 2I flip. EI pi half EI K pi right? Pi half plus k pi. It's not just that. There is an alternating signs. It depends on what k is. All right. So it all depends on this guy here. What is this? Remember, this is a cosine k pi, so you have to be careful. So this is a negative 1 to the k. If k is 1, you have negative 1. K is 2, you have 1. K is 3, and so on. It's a common factor. Now, ei pi half, what is that? We know what that is. It's just I. E minus I pi half, it's also negative I. So we got 2 i's, another 2 i's here, they simplify. Negative pi half plus k pi divided by negative 1 to the k. If I bring this negative in here, I end up with negative 1 k plus 1. Pencil is dying. Let me find another one. Quick. So I get a k plus 1 and then pi half plus k pi. This is, so it's not just pi half plus k pi. There is this alternating sign, negative 1 to the k plus 1. Now here's one for you to do at home. The part F, no problems there. Now f of z is z to the 1/4 over z plus 1, which is defined for module of z positive and argument of z. You have to pick a branch because of the 4th root of z. So argument of z will be between 0 and 2 pi. Then z to the 1/4 is exponential 1/4 times log of z, and the log of z require picking a branch. That's what I did. So you finish this at home. Find the port. It's clear.